Okay, so we will start now, right? For the last sessions, okay, we have learned about the isoparametric formulations, which are widely used for the finite element software, okay, finite element analysis software, right? So from here onwards, okay, so from here onwards, we basically have only left maybe 3 more sessions of classes, and yeah, this course will be completed, right? So roughly 3 more classes, including this, right? So probably since you would start to do the lab starting in June, right? So probably by that time, some of the sessions will be arranged during my time, maybe Monday or Thursday, right? So for those who can't attend, then you just let me know. So probably I will not run much class by that time. Okay, only maybe we will have one test, okay, which will be held face to face. Hopefully, if nothing, no more restrictions, then we will do one final test before we complete the course. All right. Okay. So today we will go through the second part of the isoparametric formulations. Basically, this one is not very related to the isoparametric formulations. Okay, it is more on how the storage of the mainly of the stiffness matrix, okay, or those matrices in the finite element methods, okay, which implemented in the software itself can be stored in an more efficient way, right? So why I would say so, okay, because just let's have some thought of it, okay? How large is the stiffness matrix can be if there is a, let's say, 50,000 bar element, okay? So if, as you know, 50,000 bar element, bar is just two-dimensional cases, right? Two-dimensional, not a beam. So probably you have two, I would say two by two matrices, okay, to represent the stiffness matrix, right? Okay, for single bar element. When you have 50,000 bar elements, meaning to say your matrix, okay, your matrix may be in a form of 50,000 times 50,000 of the size, okay, in terms of number of row, maybe 50,000, okay, and in terms of the column, also 50,000, right? So roughly around that value, okay? So how much in terms of data, okay, how much data it require in your computer? So if 50 times 50, okay, we can estimate roughly over here, okay, this is 40 times 40, is already 11.9 gigabyte, right? So 50 times 50 type of matrices, okay, it will roughly takes you at least 12 gigabyte, okay, of data, okay, or memory required, okay, to store this form of matrix, okay. So this one is only storing, okay, without doing any manipulation, meaning to say, if you want to run the software, okay, which consists of 50,000 bar element, okay, assuming that there is 50 times 50 thousands the size of the matrix itself. Therefore, this matrix will be loaded to the RAM, okay, the memory of your computer, right? So when it is loaded to your memory, meaning to say, let's say your RAM is only 8 gigabyte, meaning to say the remaining, if let's say you need 12, okay, let's say you need 12 gigabyte, right, to store this, okay? So 12 gigabyte, meaning to say your computer will need at least 12, okay? If your computer doesn't have 12, what the computer will do is if let's say your computer only have 8 GB of RAM, okay, what your computer will do is you keep loading, okay, do some process, put it back, okay, and so on, right? So this is how it will affect your performance, the performance of your computer, okay, during the simulations itself, okay. This is only a bar element. Just imagine if we increase it to a 3-dimensional type of elements, the number of equations to be solved simultaneously also will increase tremendously, okay. And also it depends on the type of data that you would want to store, right, in the matrix, okay. Usually in the form of double, okay, in most of the cases, okay, in our cases, okay, instead of integer, okay, because all these values, it can be 1.0235 and so on, right? So it is a double type of data, right? So you can imagine that only 50,000 elements, okay, it's not much in your computer, right? But it requires a lot of data or memory to be able to start to process, okay. So if you have more than one of these, your computer will need a lot of memory to actually process. But then how can this be done in a more efficient way, right? So one of the way is we call it as to compress the storage of the stiffness matrix, right? So the stiffness matrix for a linear equations that occurs are usually, okay, and always in a symmetric, okay, symmetrical form, right? Meaning to say we always have one-sided, okay, so you have 1, maybe 1, 0, and so on, okay. So this is a symmetrical way, and what it means by banded, it meaning to say it's usually in a form of one-sided, okay, one band, okay, instead of going all the way to the end, right? So if it is symmetrical, maybe this part contains values that are non-zero, okay, the rest may be already zero, right? So not by taking these observations into account, okay, therefore we could somehow compress the storage, okay, by removing all this unnecessary zero, okay, for the purpose of the calculations, okay. So we call this as the implementation of a compressed storage of the stiffness matrix. It is useful to actually it's useful to fit into the memory because the size is now smaller, okay, for sure. And then when the size is smaller, the computational would take place in a more efficient and faster, okay. So that's why it is much desirable, and most of the finite element software actually implement this type of storage, compressed storage method, okay. So in general, there are 3 ways of doing it, okay. There are banded symmetric format, okay. There are skyline format, and the last one would be this one not necessarily, it's not about how it's stored, but it's more on how the computer will load the data, okay, on how the computer will load the data and process this, right? So first we look at the banded symmetric matrix, okay. So as we say, the common characteristic would be symmetrical, okay, symmetrical, and then banded, okay. Banded means you can see only this part consists non-zero data, okay, whereas the rest is mostly zero, right? So if we take by this so-called characteristics, now we can form a symmetric banded by taking only this, okay. So you can see this is going up to 4, right? Okay, first row going up to 4, right? Then second row also going up to 4, okay. Third row also going up to 4, right? So basically it is 4, all right, 4, But then why we put 8 is because you should take into account of each of these will have 1, 2, 3, 4, something like that. Okay, 1, 2, 3, 4 data inside it. Okay, so we would use the NB equals to 8. Okay, when we see 1, 2, 3, 4 of this so-called 8 X. All right, so every single row itself only consists of maximum four numbers. Okay, maximum up to 4 numbers. Okay, the upcoming one would be 0, 0, 0, 0, right? So therefore, in this way, okay, we only group in this form. Okay, so this first row in this form, second row into this form, and so on. Okay, so immediately you can see that instead of using 24 by 24, okay, of the matrices, we have reduced it to 8 times 24. Okay, so 8 times 24 is about 3 times lesser data. Okay, three times. Okay, because 8 divided by 24 is already 3 times, right? So 3 times lesser data, okay, compared to this, right? So that's why it will reduce the memory size, as well as it is much more easier to compute. Okay, you don't have to multiply, even though it is multiplication of 0, but it still take the computer to do the multiplication for you, right? So we would call this NB as the semi-band. Okay, only the half of the band itself. Okay, semi-band NB, and this NB can be equals to the ND bracket M plus 1. Okay, so this ND is the number of degree of freedom per node. Okay, that's why I would just now I say this. There is a 1, 2, 3, 4. Okay, assuming this is only a bar element. Okay, which consists only two degree of freedom, right? So 1, 2, 3, 4, right? Okay, so it depends on mainly on the number of degree of freedom, right? So if you have 1 degree of freedom of the system, and the M is the maximum difference of the node number, okay, which we will describe later on. Therefore, if let's say this difference is 4, okay, so 4 plus 1, this gives you 5, okay? So you will get this NB equals to 5, okay? So to get 8, probably this one is maybe 7, okay? Or maybe this is 2, okay? Times 3 plus 1, okay? So this is what it means, right? So let's say now we take the degree of freedom per node is equals to 2, okay? And the M is equals to 3, okay? So now what it means by this M, okay? So this M is basically referring to the meshing, right? So you can see that the maximum difference in node number, okay? It depends on the node number itself for a finite element model, right? So you will just check with the meshing itself, okay? So let's check if we put a numbering for node, right? Take this simple examples, okay? We number it in this way: 1, 2, 3, 4, 5, 6, 7, 8, right? Very easy to number. But then in this particular mesh itself, okay? Particular mesh, in this is maybe Q4, right? So in this particular element itself, you can see that the maximum difference in numbering is 5 minus 2 is only 3, but 6 minus 1 is 5. Okay, therefore the M is 5, right? You can take the second one and check. The maximum difference is 7 minus 2, okay, which is 5, right? For the third element as well, the maximum number is 8 minus 3, which is 5. Therefore, the M equals to 5, right? So if we take M equals to 5, okay, and the ND is still 2, therefore 5 plus 1, 6, 6 times 2, 12. So the NB, the semi-band will be 12, okay, times depending on how many numbers of rows that you have, okay. If we do the numbering in the other way around, okay, let's say now we are numbering it in this way: 1, 2, 3, 4, 5, 6, 7, 8. Therefore, if we look at this particular first element, the maximum difference that you would observe is 4 minus 1, which is 3. 6 minus 3, which is 3, right? Because 4 and 5 difference is only 1, right? So the highest one, the maximum one would be the 6 minus 3. Same thing, the highest one would be 8 minus 5, which is 3. Therefore, using these configurations, the NB will be 8, right? Because 3 plus 1, 4, 4 times 2, 8. Okay, so the NB will be 8. So what we can learn from this particular examples is that we will obtain a small bandwidth, okay, by putting the node numbering across the shorter dimension. Okay, we don't put it along the long dimension. Okay, we put it along the shorter dimension. Okay, so here is longer. If you put it this way, the semi-band will be higher, the NB will be higher, okay? But if you put the numbering in this sequence, okay, in the shorter dimensions, therefore your semi-band, okay, or the bandwidth will be shorter, okay, or smaller, right? So this is how you can create a much more efficient type of storage, okay? Because the NB depends on this, right? Okay. So what we can learn that is it's very depending on the not numbering sequence. Okay, how you number it, okay, on your mesh, right? And what if we compare the execution time between these two not numbering, okay? How we can compute? What you can do is you can try it later on using this formula, right? So in general, we can estimate the execution time, okay? How much time required to actually do the calculations, okay? So when the band is not used, okay, meaning to say we use the full previously is 24 times 24, right? So if we don't use any of this, then this would be in this form of execution time, okay? But when we use the banded storage, then this become n multiplied by nb square, okay, instead of n3, right? So this n would be the so-called the numbering, right? But then we don't know this numbering yet, right? So we just assume it is n so that we can do a comparison later on, okay? So what we can see is that when we use this NB, then let's say NB square itself, okay? The ratio, okay? By taking the ratio with and without, okay? We can cancel out the n here, right? So when we cancel out the n, the upper part would be without the banded storage. The lower part is the banded storage. So we will get a ratio of n squared divided by 3 nb squared, right? So if we take an example with, like, let's say the previous one, okay? We get the NB is 8. Okay, we get the NB is 8. Therefore, what we can see is that this NBS is at the lower part, okay, lower part of a fraction. So the smaller number it is, then this ratio is bigger, right? So if you get 1, then that is the best, right? If you get 8, okay, to the power of 2, then you get 64, right? If you get 12, then the number will be getting higher and higher, right? So therefore, you can see that by reducing the semi-band, the NB itself, you can reduce the execution time, okay, by a ratio, by this particular ratio, okay, depending on how much compression of the banded that you can achieve, okay, through the numbering of your mesh, okay. Then the second method of compressed storage would be using a Skyline method, okay, Skyline method. I'm not sure if the Lisa FEA software shows anywhere about the banded or the Skyline, okay. But then they internally have implemented maybe part of it, or maybe one of this method, okay, to actually make the computational more efficient, right? They may not state it to you, but what happened is that this is what people have studied and how they can implement it in the final element software, right? So for the Skyline method, it's very similar to the banded one, okay? But then it is the way we form the Skyline, okay, now is depending on this, right? This, let's say this symmetry line is your, how should a base of it, okay, the base of your building, right? So now this building have only one story, this building have 2 story, okay, this building have 2 story, okay, this building have 4 story, right, and this building have a 4 story, and so on. So we would draw a line, okay, where those 0 is removed, okay, so this become the Skyline, okay, we call it as a Skyline method, okay. So what we would do is this Skyline is an envelope that begin from the first non-zero, okay, in every single column, okay, until the symmetry line, right? So in skylining, only the coefficient between the main diagonal and the skyline is actually stored, okay, in a column way, okay, one, right? So what the computer will do is they will store it in one single row, okay, normally in one dimensional array, okay. They will store this at the top, okay, then this one, okay, sorry, the next one, okay, from here, okay, continue, right? So this one continue, right? So it will form 1 times the summations of all these Skyline numbers, okay. So this is how they can form another way of compressing the matrix and solve them simultaneously later on, right? So in general, because we remove more zeros and also the column or the array is in one dimensional, then it's actually take much lesser storage, okay. And in terms of solving the equations, okay, it's actually more efficient than the previous banded format, right? So therefore, slowly have moved on to this Skyline, and then next would be another more efficient way of solving it, okay. We call this as a Wavefront method, okay. This Wavefront methods basically focus more on how we can make the calculations, okay, of simultaneous equations more efficient, okay, instead of storing it in the form of matrix, okay, a smaller size of matrix. This Wavefront method consider the assembly of equations, okay, for the Gauss elimination, okay. Remember, in Gauss elimination method, mainly is to solve simultaneous equations, okay. In the computer system, okay, or in the program itself, the final element software program itself, the program actually employ this Gauss elimination method, which is the numeric type of numerical methods, okay, to solve all these simultaneous equation, okay. But the only difference is that in this Wavefront method, okay, we take into the account of how the sequence of solving, okay, of these equations can actually minimize the data needed to be loaded for the calculations, right? So in this method, the numbering of element now, okay, not okay, numbering of element are more important. Okay, so the numbering can be like what you want, okay, but the numbering of element is more important. Okay, we would want to number it in a sequence. Okay, this element is element number 1, element number 2, 3, and so on. All right. So why we need this to be numbered in this sequence, okay, is because when we trying to solve for the solutions, okay, the arrangement of the equations or the assembly of equations actually being grouped by the element number, right? So if you have element number 1 and element number 2 next to each other, okay, so therefore we can actually solve for, let's say, this common nodes fast, how would say, not faster, but you can find the next so-called equations to get the solution much more quicker, right? So to illustrate that one, okay, let's say we take into the account the element number 1. So in element number 1, there are 4 unknown, right? So there are 4 nodes to be solved, okay, not 1, 2, 3, 4, okay, element number 1, there are not 1, 2, 3, and 4 to be solved, okay. So usually, let's say at this side we have the boundary condition, okay. So if you have a boundary condition here, meaning to say when you load these 4 equations related to this 4 node into the software, you can do, remember in previous few lecture we do a partitioning, right? So that partitioning actually looking for a group of matrix that you can solve it easily, right? So you can see that here, if we have this boundary condition, we will solve for not 1 and not 2, okay. Okay, so we can say that not 1 and not 2 has been eliminated because we already get the solution for it, leaving not 3 and not 4, okay, unknown, right? Then when we look into the element number 2, what is loaded into computer would be 3, 4, 5, and 6, okay, 3, 4, 5, and 6, okay. But when we have these 4, all right, and they are related, they are common, okay, between these two elements. Therefore, again, these two can be solved, okay, because we have find the simultaneous solutions between these two set of elements, okay, and we found the common solutions or the converged solution for node 3 and 4. Therefore, we say node 3 and 4 now is solved and eliminated, right? Then same thing when we repeat for node number 3, element number 3, node 5, 6 can be solved, okay, then followed by 7, 8, right? So you can see that the number of node, okay, meaning to say each node may represent 2 equations, okay. So the number of node involved is only maximum 4, okay, by using this sequence, okay, by using this sequence, okay. What if we don't use sequence, okay? To see the effect is that if we number it 1, 3, 1, 3, 2 in this way, what happens is that same concept, all right? We have a boundary condition over here, let's say, okay? So element node number 1 and 2 will be solved, okay, at the first node, okay? At the first element, node 1 and 2 will be solved and eliminated, okay, leaving 3 and 4, okay, 3 and 4, right? Then come to node number 2, okay. Why we jump to node number 2? Because in the computer, the solutions is usually in the sequence of element, okay. We will solve for element 1, 2, 3, and so on, right? Computer is not smart enough to search which one should solve first, okay. They will just follow a numbering. So therefore, this one solve, then they will go for the element number 2, right? So element number 2 now, these 3 and 4 still unknown, right? So they are still there to be solved, okay? But then 5, 6, 7, 8 is loaded into your computer memory. So therefore, at this particular stage, okay, there are 6 node data to be loaded and try to solve it simultaneously, right? But then since this is at the free end, let's say, okay, at the free end, 7 and 8, maybe you have about another boundary condition. Let's say displacement is 0, there are force and other things. Therefore, not 7 and 8 have been eliminated and solved, okay, leaving the other 4, right? Leaving the other 4. Therefore, by seeing this one, okay, you can see that the maximum number of nodes involved in one particular set of element, okay, to be solved is 6, okay, instead of 4, right? If you jump more, okay, then this number of not living unsolved will be getting greater and greater, right? This is why this wavefront have is a method where you tell the computer, okay, which one to solve faster, okay? If you number in this way, okay, then you get this solve first, okay, this one can be solved next, and so on, right? So we say that the first element eliminated, okay, then next contributions of the stiffness will give you, okay, the partitions or group of data, okay, that are sufficiently solved, okay, for the next element, right? So for based on these observations, therefore we can say that the consecutive element numbering should be done across the structure, okay? Again, in the directions spanning the smallest number of nodes, okay? From the smallest number of nodes, okay, to the bigger one, right? So this is how you can make things much more efficient, right? So this wavefront methods is computationally more efficient again than the banded matrix, okay? Even maybe more efficient than the Skyline as well, okay? Because of the way we load the data into memory and solve it, okay, part by part in the partition way, right? So in the wavefront method, this block of zeros coefficient are not stored or processed. Okay, you don't see that they are actually stored or processed. It's like you are doing the partition for this group of nodes only. Okay, bring it in, solve it, whatever not solved, okay, store, remain there, and bring another new set and solve it. Right. So this is a way of doing it in a computational way. Right. So any questions so far? Okay, so you may try this exercise or examples at home, right? It may increase your understanding on what we have learned so far, okay? Especially on how to find the stress, right? So any questions so far? While I speak, yeah.
No questions, sir.
All right. So if no questions, then I will go to the next chapter, okay? Which I will not cover everything today, okay? I will stop at 3 p.m. later, right? So the rest we will continue in the next lessons, right? Let's start. Okay. Right. So next we would see on the applications, okay? So far what we need to cover have been gone through, okay? From the early ideas of what is FEA, what is FEM, okay, then we talk about the software, okay, what are the criteria, maybe the asymmetry, the symmetry, and other things that can be implemented in the FEA software. Then from there onwards, we start to move on to the first the bar element, then beam element, okay, which is I would say is a one-dimensional type of element. Okay, then move to the two-dimensional type, okay, which we covers like the plane stress and plane strain, okay, using CST and Q4, okay. In this course, we will not touch on the three-dimensional, okay. So the concept is still similar, okay, and you can see that from these four type of element that we have gone through, five type, from the spring, bar, beam, CST, Q4, five type, okay, you can see that every time we only form the stiffness matrix, okay, and this stiffness matrix actually represent the characteristics of the behavior of the model, okay, that you intend to simulate, right? So if it is a structural, then this particular stiffness matrix model would represent the stiffness, okay, the Hooke's law, okay, where the Hooke's law can apply, all right? Then using the same concept, we actually can expand it, okay, to three-dimensional, and now is where we try to explore on other applications. Okay, so far we only talking about structural analysis. Okay, we used to analyze the deflections, okay, or the displacement of cantilever beam itself, right? Okay, so this chapter will be more on how we can solve for the thermal fluid. Okay, same thing for the coming chapter. Okay, also on the thermal fluid, right? So this chapter will be on the thermal. The next chapter will be on the fluid part, right? Okay, so here are two particular links, okay, that you can try. Okay, I'm not sure whether it's still accessible or not, okay, but these are the, how should I say, the manual, okay, that you can go through. Okay, so most of the final element software, okay, especially those establishment, they have a benchmark guide. Okay, they will do some type of benchmarking with experiment, or maybe some research, okay, and to check whether the software calculation is efficient or accurate or not. Okay, we call it as a benchmarking, right? So there are some benchmarking guide or to show you, right? Then also you can try to check this link, okay, from UTM by Dr. Ridwan, okay, on the same course, okay, finite element methods. Okay, so you can see that the topic, whether what we have covered is similar or not, right? Whether we have covered more or less, okay, as compared to other universities. Okay, so here is how we can extend the finite element methods, okay, into different type of applications. Okay, mathematically, the finite element methods can be developed to cater for various type of applications, okay, in general, right? For examples, just imagine previously we used for structural, right? So how we can apply it for thermal applications is that the we would say it is in the field of heat conduction, okay, because we know that most of the heat is being transferred through the solid, okay, through the solid, not through the air, right? Therefore, most of the time we would say it is a heat conduction type of analysis or thermal analysis, right? So for this heat conductions field, the equations involved is actually K delta square T divided by delta X square plus delta square T, okay? This T represent temperature and this XY represent the two-dimensional directions, okay? In the X directions and the Y direction, okay? Plus Q equals to 0, okay? So this is basically a heat conduction equations, okay? The Fourier equations, okay? That involve the gradient of the temperature, okay? Across the dimension X and Y, okay? Multiplied by a constant K, okay? Where this K is the thermal conductivity, okay? Just like the structural, you have to provide the parameter E, right? Remember, E represent the Young modulus, okay? To describe how the material actually react, okay, to the force or stress, okay? Okay, and there that is the relation. So similarly for the heat conductions, we use this thermal conductivity K, right, to represent the behavior of the heat being transferred across the material itself or the model itself. Okay, we call this as a thermal conductivity, and the variable that we will produce is the temperature. Okay, we may input one temperature and see how this temperature will change. Okay, so same thing with the structural, we input Young modulus and our variable will be the displacement, the strain itself, okay? How the force, okay, will change the characteristics of the displacement, okay, and the strain. So in this case, our variable will be T, okay, in terms of T for the heat conductions, okay. For the boundary conditions, we can apply three types, okay. So we may apply the initial conditions. Initially, maybe we say it is in the room temperature, or initially the model is in maybe in ice box, you may put 0 degrees Celsius, okay, or 3 Kelvin, right? Then next, we would also can include this, I would call, is this the rate of heat loss, okay? The rate of heat loss, okay? And also this one represent the conduct, not convections, okay, of the model, okay, how it can be, how the heat actually lost, okay, from the surface, okay, through conductions, okay. So we have this type of boundary conditions to be implemented to the model, okay. So basically very similar, okay. Same thing for the flow, we have similar streamline equations, okay, streamline equations, and the variable is the stream, okay. Then also we have the Q. This one is the heat input. This one is the so-called the flow input, right? The force in the flow, right? You can also set the initial stream functions, okay? For electrical potentials, also we can use similar way, okay? Same type of equations, okay? Same form, right? Power 2, power 2, power 2, okay? Power 2, similar form, okay, and equals to minus P. Okay, if we remove or if we move this over here, then this is plus P equals to 0. Okay, again, very similar form. Okay, where the variable is electrical potential and the parameter is the permissivity. Okay, again, we have the boundary condition that we can set as like inertial U, okay, and also the boundary conditions of no losses, okay, equals to 0, okay, through the boundary, right? Even we can expand our FEM application to the acoustic, okay, again, similar differential equations, okay, plus this part is the input, okay, or the input of the acoustic to your system, okay, which mainly depends on the wave number and the pressure, right? So that would create the changes to your acoustic system. Okay. Again, boundary condition, initial boundary condition, and others type of boundary condition. So you can see that by observing these equations, they are basically similar to the equations that you use to describe the structure, right? Therefore, since they are similar form of equations, similar form of differential equations, we can expand, okay, the usage of the finite element methods to different field, okay. So now we would look into the one-dimensional heat conduction formulations, okay. So again, one-dimensional here is referring to only one way, okay, not the y or z directions, right? Only x directions, okay. So when we start to derive, we do not consider
Guys, apa jadi guys?
I don't know.
Kau punya lens lag-nya atau macam mana?
Aku pun dah tahu. Aku ingat aku pun lag. Dokter Cho ada nggak masih?
The left
Ada.
Aduh.
Line-nya Mas ni pun lambat juga nih.
Biasa dokter dalam ni.
Ada sudah.
Ada.
Ada saga? Ya, cek dulu.
Beda.
Oi. Mana ada? Oh, di sik.
Oke, kelas dismiss.
Mati karen kah di FKJ?
Masalah line UMS.
Ya, pas tuh. Aduh.
Kawan aku pun ada problem juga kelasnya.
Apa aja yang enggak problem kalau UMS nih?
Nggak apa, sabar lah. Ya, aku mau kasih kena orang loh.
Oke,
Ryan
saya bilang
Noel.
dismiss, saya bilang.
Brian Noel.
Kelas dismiss.
Bah. Bah, hati-hati kamu yang isolasi itu.
Jaga diri semua.
Jadi
Kelas dismiss. Saya bilang line rusak.
Bye, bye Jun.
Bye.
Okay.
Bye,
Okay.
bye.